Okay, let's go through an example of working to find a confidence interval for a mean. So here's a typical type of question you'll come across. In this particular scenario, they give you a list of data, right? A table of data set where these are all averages, right? Taken from different countries last year. And it's the carbon dioxide emissions in metric tons per capita. And then they want you to compute a 94% confidence interval to estimate the mean carbon dioxide emissions for all countries. Now, some other interesting stuff they tell you is that in 2004, the mean was 4.87 per capita, but they don't tell you anything about what the standard deviation was. So we don't know the standard deviation of the population, right? Because the population are all countries. We just have a sample here of, I think it's about 34 or so of them. So the first thing I would suggest is to copy your data into Excel. Now, depending on what kind of interface you have, uh, copying data into Excel can be tricky sometimes. Now, it turns out that if you're dealing with WAMAP, like I am with this example, in order to copy this table, if you just come up here and start your cursor at the title and highlight like this, it's not going to work. If you then do, Control C, Control V into Excel, it puts everything in one cell and it doesn't work. What you have to do is put your cursor above the table and then you're kind of highlighting the whole table. Then do Control C. Then come over here and do Control V, and then you'll see that you get everything the way it's supposed to be. Now I'm going to go ahead and kind of just clean this up so we can see everything. There we go. Okay, so that's how to get your data into Excel is you just have to make sure that you're highlighting above the table. And like I said, depending on the interface, if you're getting from a different website, you might have to do just the table. Just, try a couple different highlighting techniques until it pastes into Excel properly. Okay, now, since they're asking us to calculate a confidence interval for the mean of our population, then the parameter, remember parameter deals with population, is the mean of the population, and that's always the Greek letter, so that should be mu. And then the wording is, of course, we're just doing the mean carbon dioxide emissions of all countries. Now this one, they're just asking us to figure out, okay, do we have numerical data or not? Yes, we've got quantitative data. And if we have quantitative data, then there are certain things we need to make sure. Well, since we're doing a confidence interval, we don't have to worry about this stuff, right? This n times p greater than 10 and or 1 minus p. And so this one and this one would be if we were doing a, um, a normal approximation to a binomial. And we don't have a binomial, remember? So those don't apply. But we do have quantitative data. And when we have quantitative data and we want to do any kind of sample distribution approximations, then the central limit theorem tells us that one of two things has to happen in order for us to guarantee that our sampling distribution will have a normal curve shape so that we can, do these kinds of things. You can't do a confidence interval unless your sampling distribution is on a normal distribution shape, because if it's all skewed and stuff, then all of these, theories don't apply. So one of two things has to happen for us basically to do any of these kind of inferential statistics, confidence intervals, hypothesis testing, all that kind of stuff when we're dealing with quantitative data. And that is that we either have to know that the population we're sampling from already has a normal shape, a normal distribution. Because if that's the case, then any size sample you take from it will create a sampling distribution that is normal. Or we have to make sure that our sample is at least 30 or bigger. Because if you have a size of 30 or larger, then regardless of what you're sampling from, the sample distribution that is created by all samples of size 30 or more will always be a normal curve. And that's basically the basic tenets of the central limit theorem. So in this case, we know that we need to make sure that our sample is greater than or equal to 30, or we're pulling from a normal population. Now, they didn't tell us anything about if the population of carbon dioxide emissions was normal, but we have a sample that's bigger than 30, because if you come down here, you can see that we landed on 35, which if you subtract the first one because it's the title, we have a sample of 34. So we know that we have satisfied that rule. The other thing we need to make sure is that we don't have any outliers in our data being our sample, because if our sample has outliers, it's going to mess things up. It's going to completely skew our results, and we're no longer going to be able to kind of use the idea of the central limit theorem to let our sample give us a good approximation, a good guess of what's happening in the population. And then the other thing is we need to know whether or not they tell us sigma, right? Greek letter sigma tells us a parameter, and that is the standard deviation of the population we're sampling from. They gave us the mean of that population, but they did not say anything about the standard deviation, which is usually the case. You very rarely know the standard deviation of the population you're sampling from. So sigma is unknown. The rest of this stuff, these are all, things that are trying to trip you up, thinking that it's binomial when it's not, and all sorts of other stuff. Now, if sigma was known, then we would be doing all of these computations on the standard normal curve, the z curve. But when sigma is unknown, as it is here, then we're going to do everything on the student's t as in Thomas, curve. It looks just like the normal curve as far as it's a bell shape, but it's just slightly different, and it takes into account that we don't know the standard deviation of our population. So that's basically what this is telling us, whether we're going to use the t or the z, and in this case, we're going to use the t. Okay, so then they ask us to check those assumptions, right? Is sigma known? No, it is not. Then they want us to calculate or create a box plot from our data, because we're basically checking to see if we have outliers, right? If we have a really long tail on one of these, then that would mean we have outliers. So we need to make sure that whichever one of these matches our data, that it has to be somewhat symmetrical-ish, right? So it doesn't have any obvious outliers. So we're going to need to calculate, right, min, max, Q1, median, and Q3, basically the typical 5-number summary, in order to see which one of these fits our data and to see if our data is normal. Now, there's other ways to do this, right? There are ways to do normal quantile plots. There's all sorts of stuff that they talk about that are checks for normality, and it's just ways to make sure that your sample that you have is roughly normal, that it doesn't have any outliers. Okay, so let's do this in Excel. We just have to calculate all of those, bits and pieces, min, max, and so on and so forth. And you can do all of it with the same function, the equals quartile function. And, whether you want to do the exclude or include, it really doesn't matter. You can just use the old standard one if you're using the old one. And then all you do is the array just means tell me the data that you want me to calculate the quartile on. So you just highlight all of your data. And then you do comma. And then here it tells you 0 gives you minimums, right? So it's asking for the quartile. 0 would give you minimum. 1 would be the first, right? Median, third, and max. So we're just going to go 0. And then I'm going to go ahead and copy this and put it here and paste it. Oop, sorry. That's not what I wanted to do at all. Let's just do this. We'll put a $sign in here to make these numbers stick. And then we can drag this. 2, 3. There's 5 of them. 1, 2, 3, 4, 5, right? So this is going to be our min. This is going to be Q1. This is going to be our median. This is going to be Q3. And this could be our max. And all we have to do is go back in here and change this to a 1, change this to a 2, change this to a 3, and change that to a 4. So now we can see roughly what these values should be, right? 1.4, 2.7, and so on and so forth. Now they might differ slightly from what the question is asking, because it depends on if you're doing, if you're using quartile inclusive, quartile exclusive, if you're running quartiles in Excel versus if you're doing the quartile function in a TI graphing calculator, or if you're using the standard formula for finding the locators, the whole percentage times your sample size gives you the locator, and then you got to sort your data and blah, blah, blah. There's a bunch of different ways to compute quartiles. And unfortunately, you will get slightly different results depending on the technology you use. So it might be the case that ours doesn't perfectly match, but we should be able to at least find something similar. So we can see that all of these have 0.06, right? And all of them have 911 for 9.11 for the minimax. The Q1 should be somewhere around 1.42, 1.43. So here's 1.42, 1.42, 1.42. So we can see that those are correct, right? And this one's now out. The median, 2.74. So that's not close. That one is, that one is. So now we're down to this one or this one. And then a Q3 is 5.86, right? So it's obviously this one. So we can see that this would be our answer. And if we look at this, sure, this one's longer, but it's not hugely longer, right? Sure, the median isn't perfectly in the middle, but it's not tucked up against one side. So is it perfectly normal? Heck no. But it's close enough that we can say there are no outliers, right? No, the modified box plot shows no outliers. Now, if we really wanted to test for outliers, right, we could do the whole IQR thing. Let's put it over here. And remember, your IQR is simply, it equals Q3 minus Q1. And then you're supposed to do 1.5 times the IQR. So that's going to equal this times 1.5. And then you add that to the Q3 and you subtract it from the Q1. And those are your cutoffs. Anything that is outside of that is considered an outlier. And some people would even say 1.2 to kind of find mild outliers. So we could even change this to 1.2 if we wanted to. And of course, change it here. Now, if you add this to Q3, right, so this is going to equal this plus Q3, that's kind of our upper bound. And if we subtract it from Q1, it's going to equal Q1 minus this. That's our lower bound. And basically what it means is outliers would be anything that falls beyond those cutoffs. So anything smaller than -3, which we know is impossible, right? Because, I mean, if we're measuring something in the real world, you can't get a negative. We saw, for instance, that our smallest one was 0.06. So we know nothing's going to go beyond the lower bound. And then above the upper bound would mean it'd have to be bigger than 11.1, and we saw our maximum was 9.11. So again, we've kind of verified that there are no outliers in our data set. Okay, so then that tells us that our sample size, right, is 34. That's what I told you before when we looked in Excel, which is, right, greater than or equal to 30. So we're checking the next assumption. So is it reasonable to assume the population is normally distributed? Not necessary to check since the sample size is greater than 30, right? You can never assume the population is normally distributed. That's something you have to kind of know. Okay, so now we've checked all the conditions, all the assumptions. They are all met. So now we know that we can use a t-interval, and the reason why we're using a t, right, and not any of these other things, I'm surprised, obviously we're not doing proportion z's, and they should have just had a z interval as one of the options, because that would have been a simple mistake to make. You can't use the z-curve unless you know the standard deviation, which we don't. So now our interval and our point estimate, so basically now we're going to talk about the symbol and value of the point estimate. Remember, the point estimate is just the piece of data, the statistic that we get from our sample that estimates the thing that we're trying to do in our population, our parameter. Well, we're trying to do the mean. So now in our sample, the mean is X bar, and it's still metric tons per capita, and then we have to compute X bar, and that would be something we'd have to come over here and go, equals average, double click, highlight everything, and there's our average, 3.405. And if they want it, to 3 decimal places, it's best to go up here and let Excel do the rounding for us. There's 3.405. The interval estimate for mu, right? We're trying to find an interval for mu is, and then this is where we're finding our interval, and they're just putting metric tons per capita after each thing. So this is where you have to find your confidence interval. You have to basically calculate your margin of error and add and subtract it from your mean. Well, how do we do that? Well, that involves, if you have a TI graphing calculator, you can actually do it really easily, or you can use some formulas, or you can kind of calculate it in Excel. It just depends on how you want to do it. All right, in Excel, it's super easy. First of all, we're going to need the standard deviation. So you could actually do this as part of the formula or function that you're going to use for confidence interval, but it might be easier to just do standard deviation.s for sample, right? Highlight your data, and then that's our standard deviation for our sample. Now the margin of error is really easy. Equals, start typing in CON for confidence interval, and look at that. It does confidence on a T, which is what we want because we're on the T curve. Confidence norm would have been if we were doing the normal Z curve. That's because we would have known the standard deviation, but we didn't of the population. Okay, so it asks for alpha. Now, alpha it depends on the technology you use. So in this particular question, they asked for a 94% confidence interval. For this example, they wanted a 94% confidence interval. And alpha is always your error. So in this case, 100 minus 94 is 6. But if you think of a confidence interval that's centered in the middle of the curve, that's the 94% in the middle, your error is your 6%, so you have 3% in each tail. Sometimes your technology will want the 3%, basically alpha over 2. In Excel, alpha is just all of alpha, so it's 0.06. So that's just something you need to know about, how your technology works. Then it wants the standard deviation, so we're going to click on the square where the standard deviation is. And then it wants the size, which is the sample size, which we know is 34. And then there's our margin of error. Now, the upper bound of our confidence interval is simply just going to be our point estimate, our mean, plus our margin of error. And then our lower bound is simply just going to equal our point estimate of the mean minus our margin of error. And there are our two bounds, right? Our confidence interval goes from 2.539 up to 4.272, and you can see that's exactly what they want, 539 and 272. Okay, so that's how we would compute it in Excel. If you want to do it, on your TA calculator, you got to go into the stats and I think it's in the distributions menu or in the, I don't know. It's in one of those. You can do it. Well, all right, I'll do it for you right now. Okay, so on the TI, you want to go to Stat, and you want to go over to Tests. I can never remember it's called Tests. And you can see that here's where you can do Z-test, T-test, and then doing with a T-test or a Z-test for samples and 2 samples, and then proportions. And then here you go. The Z interval would be if we're doing a confidence interval on the Z curve, but we're doing a confidence interval on the T curve, so we choose that one. And then here it wants you to either input the data or input the stats. So if you wanted to input the data, that's where you'd have to go and manually type in all 34 of these into list 1. Oh, we don't want to do that. So instead we're going to choose stats. And then it changes, right? Instead of asking for list one, it now asks for, well, what were your results from your data? What were your stats? And those will be calculated very easily in Excel. By doing this, it saves us from typing stuff in and having typos. Now, here is one thing to worry about. We don't want to type in just a couple decimals. We want to have a lot of accuracy when we're putting our stats into the calculator. So make sure that you give yourself a lot more decimal places here, right? So, go out a bunch, do the same thing here because we're going to need the standard deviation, go out a bunch. Now we can put those in there. All right, so the mean 3.40529411176. That should be enough to be accurate. Our standard deviation 2.59363. 1, 2, 3, 4 zeros, 1, 2. Again, that should be enough to get us, accurate to within 3 decimal places. And then we have a sample size of 34. Okay, our confidence level here, remember, was 94%, so 0.94. So they don't ask for alpha here; they ask for just the confidence level. So again, it depends on your technology, and then you tell it to calculate, and there it is. There's your lower. And you can see that if we round to 3, we're going to get the 539. And if we round to 3 here, we're going to get the 272. Okay, so that's how you can do it with a TI as well. The last thing is our conclusion. What does this tell us? Well, what is our percent confidence? Well, our percent confidence is the 94% that we just created, right? We created a confidence interval that was 94% of our, data width kind of stuff. We're 94% confident that the mean carbon dioxide emissions of all countries last year is between our lower and our upper. That's basically what a confidence interval tells us, is that we're this confident that the thing that we're trying to estimate, in this case, the mean of our population, is within the bounds of our interval that we just calculated. So we think the mean carbon dioxide emissions for all countries last year is somewhere between 2.539 and 4.272, because that was the interval that we calculated at a 94% level. Okay, so that's all the nuts and bolts for doing confidence intervals, in Excel and also in the TI. Hope that helps.